Hi, welcome back. Today we are doing section 1.3 scientific methods. Okay, figure 1-8 shows students working together on an experiment in a laboratory. You know that each person in the group probably has different ideas about how to do the project and a different part of the project that interests him or her the most. Having many different ideas about how to solve a problem is one of the benefits of many people working together. Communicating ideas effectively to one another and combining individual contributions to form a solution can be difficult. And those are some of the difficulties that groups will encounter, but it's very important that we learn how to work through those. Okay, so today we're going to identify the common steps of the scientific method, compare and contrast types of data, compare and contrast types of variables, and describe the differences between a theory and a scientific law. Here's your vocabulary that we're looking for, and you might want to pause and write these down in your notebook as we go through. Scientific method, qualitative data, quantitative data, hypothesis, experiment, independent variable, dependent variable, control, conclusion, model, theory, scientific law. Okay, so a systematic approach. Scientists approach their work in a similar way. Each scientist tries to understand his or her world based on a personal point of view and individual activity or creativity. Often, the work of many scientists is combined in order to gain new insight. It is helpful if all scientists use common procedures as they conduct their experiments. Okay? A scientific method. Okay? Notice that this is one of your vocabulary words. A scientific method is a systematic approach used in the scientific study, whether it's chemistry, biology, or physics or other sciences. It is an organized process by which scientists do the research. So it is an organized way that scientists do the research, and it provides a method for scientists to verify the work of others. Okay, so you should be recording that down. You should be recording that down as your vocabulary word. An overview of the typical steps of scientific method is shown in figure 1-9. These steps are not used as a checklist to be done in the same order each time. Therefore, all scientists must describe their methods when they publish the results. If other scientists cannot confirm the results after repeating the method, then doubt arises over the validity of the reported results. So let's look at figure 1-9. Okay, here is figure 1-9. Okay, we're going to talk about each of these. We have observations, hypothesis, we perform our experiment, you might revise your theory, and then if enough people test it, it could become a theory or a scientific law. Okay, so those are the steps of the scientific method. Okay, observation. You make observations throughout your day in order to make decisions. Scientist study usually begins with the simple observation. An observation is the act of gathering information. Quite often, these types of observations scientists make are called qualitative data. Information that describes color, odor, shape, and some physical characteristics. In general, anything that relates to the five senses. And qualitative, how something looks, feels, sounds, tastes, or smells. So again, this qualitative data is a vocab word, so you're going to be writing down this definition. So I like to think of qualitative data as me buying a shirt. When I go in and I buy a shirt, I'm touching, I'm feeling, I'm like, ooh, that feels good. It looks good. Okay, so that's a qualitative data because I can feel, touch, smell. Okay, and it's kind of an opinion based. but it's more from the five senses. There's no real data numbers that are related to it. It's all about how it feels, smells, tastes, your five senses. Okay? Chemists frequently gather another type of data. For example, they can measure temperature, pressure, volume, the quantity of a chemical formed, or how much a chemical is used up in a reaction. The numerical information is called quantitative. So quantity, you know how much is there. It tells you how much or how little, how big, how tall, how fast. Okay? So there is a number associated with quantitative data. You have 5 M&Ms. Okay? I can count them. I have a number. So what kind of qualitative and quantitative data can you gather from figure 10? So let's look at figure 10. Okay? So we could count how many teeth he has. That would be a quantitative data. Okay? You could say he looks bumpy. That's a feeling, okay? He's warm. So if you're making that observation but not giving a number, that's qualitative. If I say that his body temperature is 99 degrees, that gives me a number. So that's the difference between a quantitative and qualitative. Qualitative is senses. Quantitative is how much of something, okay? Our next step is hypothesis. Let's return to the story of the two chemicals that you read about earlier. Even before quantitative data showed that ozone levels were decreasing in the stratosphere, scientists observed that CFCs were found there. Chemists Mario Molina and F. Sherwood Rowland were curious about how long CFCs could exist in the atmosphere. Molina and Rowland examined the interactions that can occur among various chemicals in the troposphere. They determined that CFCs were stable there for long periods of time, but they also knew that CFCs drifted up into the stratosphere. They formed a hypothesis that CFCs break down in the stratosphere due to interactions with ultraviolet light from the sun. In addition, the calculations they made led them to hypothesize that a chlorine particle produced by this interaction could break down ozone. So again, here is a vocab definition for us. A hypothesis is a tentative explanation for what has been observed. Molina and Rowland's hypothesis stated that they believed to be happening even though there was no formal evidence at that point to support the statement. Okay, experiments. A hypothesis means nothing unless there are data to support it. Thus, forming a hypothesis helps the scientist focus on the next step in the scientific method. The experiment. An experiment, again, this is another vocab word. An experiment is a set of controlled observations that test the hypothesis. The scientist must carefully plan and set up one or more laboratory experiments in order to change and test one variable at a time. A variable is a quantity or condition that can have more than one value. Suppose your chemistry teacher asks your class to use the materials shown in figure 1-11 to design an experiment in which to test the hypothesis that table salt dissolves faster in hot water than in warm temperature. Okay, let's look at figure 1-11 here. Okay, so we're setting it up. We have the weight of the table salt. This is going to weigh it. Then we have something that will that you'll be able to heat up the water. Okay. Because temperature is the variable that you plan to change, it is the independent variable. Okay, so we might say that's also the manipulated variable. Okay, again, this is a vocab word. Your group determines that a given quantity of salt completely dissolves within 1 minute at 40 degrees C, but the same quantity of salt dissolves only after 3 minutes at 20 degrees C. Thus, temperature affects the rate at which salt dissolves. This rate is called the dependent variable. Okay, so again, this is another vocab word. Because Its value changes in response to a change in the independent variable. Although your group can determine the way the independent variable changes, it has no control over the dependent variable and how it changes. What other factors can vary in your experiment? Would the amount of salt you try to dissolve make a difference? The amount of water you use? Would stirring the mixture affect your results? The answer can be yes to all of these questions. You must plan your experiment so that these variables are the same at each temperature, or you will not be able to tell clearly what caused your results. In a well-planned experiment, the independent variable should be the only condition that affects the experiment's outcome. A constant is a factor that is not allowed to change during the experiment. The amount of salt, water, and stirring must be constant at each temperature. In many experiments, it is valuable to have a control. That is a standard for comparison. In the above experiment, the room temperature water is the control. The rate of dissolving at 40 degrees C is compared to the rate at 20 degrees C. Figure 1-2-12 shows a different type of control. A chemical indicator has been added to each of these three test tubes. Acid is added in the middle test tube, and the indicator turns yellow. This test can be used as a control. Compare the other two tests with control. Does either one contain acid? The interaction described between CFCs and ozone in Molina and Rowland's hypothesis takes place high overhead. Many variables are involved. For example, there are different gases present in the stratosphere. Thus, it would be difficult to determine which gases, or possibly all gases, are decreasing ozone levels. Wind, variations in ultraviolet light, and other factors can change the outcome of any experiment on any given day, making comparisons difficult. Sometimes it's easier to simulate conditions in a laboratory where the variables can be more easily controlled. An experiment may generate a large amount of data. This data must be carefully and systematically analyzed because the concept of data analysis is so important. You will learn about this in the next chapter. Conclusions. Scientists take the data that they have analyzed and apply them to the hypothesis to form a conclusion. Again, this is a vocab word. A conclusion is a judgment based on the information obtained. A hypothesis can never be proven. Therefore, to say that the data supports a hypothesis is to give only a tentative thumbs up to the idea that the hypothesis may be true. Its further evidence does not support it. Then the hypothesis must be discarded or modified. The majority of hypotheses are not supported by the data, yet still yield new information. Molina and Rowland form a hypothesis about the stability of CFCs in the stratosphere. They gathered data that supports their hypothesis and developed a model in which the chlorine formed by the breakdown of CFCs would react over and over again with ozone. You must realize by now a model is visible, verbal, and or mathematical explanation of experimental data. A model can be tested and used to make predictions. Molina and Rowland's model predicted the formation of chlorine and the depletion of ozone. It is shown in figure 1-13. Another research group found evidence of interactions between ozone and chlorine and taking measurements in the stratosphere, but they did not know the source of chlorine. Molina and Rowland's model predicted a source of chlorine. They came to the conclusion that ozone in the stratosphere can be destroyed by CFCs and that they had enough support for their hypothesis to publish their discovery. A theory, and the explanation has been supported by many experiments. You may have heard of Einstein's theory of relativity or atomic theory. A theory states a broad principle of nature that has been supported over time. All theories are subject to new experimental data and can be modified. Also, theories often lead to new conclusions. A theory is considered successful if it can be tested to make predictions that are true. In 1985, the announcement of the British Antarctic Survey that the amount of ozone in the stratosphere was decreasing led Molina and Rowland's hypothesis that chlorine from CFCs could destroy ozone Further support. Scientific law. Sometimes many scientists come over and over again to the same conclusion about certain relationships in nature. They find no exceptions. For example, you know that no matter how many times skydivers leap from a plane, they always wind back on Earth's surface. Sir Isaac Newton was so certain that attractive forces between all objects